Imagine a car that never needs to be plugged in, never needs gas, and can supposedly generate its own power indefinitely. Today, we're putting Maxwell Chikumbutso's self-charging electric vehicle to the ultimate test. What we found might completely change the way you think about energy, cars, and the future of transportation. Stick around, because we've uncovered 7 results that were as surprising as they were shocking. First, the moment we started the car, there was an immediate sense of disbelief. Could this tiny prototype really hold enough power to move a vehicle without any external charging? The acceleration was smooth, almost eerily silent, unlike any electric vehicle we've tested before. Our instruments recorded the initial battery levels, and the readings didn't budge as we drove around the block. That was our first jaw-dropping finding. The energy consumption appeared almost negligible. By the second test, we tried pushing the limits with a longer drive around hilly terrain, testing how it would handle strain. Most electric vehicles lose efficiency quickly in these conditions, but Chikumbutso's car seemed almost to defy physics. The battery meter barely dipped, giving us our second surprising result. Energy retention under stress was far beyond what conventional EVs achieve. Then came the acceleration test. A standard EV takes a moment to deliver peak power, but this self-charging model responded instantly. We recorded our third shocking finding. The torque output was incredibly stable, even as the car sustained higher speeds. It felt as if the car was drawing from an invisible reservoir, silently feeding power into the motor with almost no loss. Curious, we moved on to regenerative behavior. Most EVs regain some power when braking, but what about this one? As we tested braking and coasting, we noticed the battery actually increased slightly, something we weren't expecting. Our fourth finding: the vehicle didn't just maintain energy, it seemed to generate more under certain conditions. Next, we examined efficiency at different speeds. On highways, most electric cars suffer from rapid battery drain, but Chikumbutso's vehicle continued to cruise for miles with minimal impact on power. The fifth result was clear. This wasn't just a city car. It could theoretically handle extended drives without ever needing a recharge. We couldn't resist testing auxiliary systems, lights, air conditioning, and infotainment. Surprisingly, the power draw from these features was almost invisible. Our sixth finding: even with multiple systems running, the battery remained virtually unaffected, challenging what we know about energy limitations in modern vehicles. Finally, we looked at long-term sustainability. Leaving the car running and monitoring the energy levels for hours, we observed subtle but consistent gains in battery capacity. That was our seventh and most astonishing result. The car didn't just conserve energy, it seemed to create it. As we dug deeper, questions started piling up. How does this technology actually work? Could this really be the breakthrough that solves the energy crisis? And more importantly, is it scalable to the vehicles we use every day? The implications are huge, not just for electric cars, but for the way we generate and consume energy on a global scale. Imagine cities powered by cars that feed electricity back into the grid. Imagine reducing fossil fuel dependence almost overnight. And yet, for every astonishing result, there were still mysteries we couldn't fully explain. What we did next was perhaps the most daring part of our experiment. We decided to push the car beyond normal driving conditions, simulating real-world stress tests that most EVs fail under. Steep inclines, heavy loads, and continuous stop-and-go traffic. Conventional wisdom would predict rapid battery depletion, but this time, the results were unlike anything we'd ever seen. The car not only maintained performance, it seemed almost unaffected by the added strain. Curiosity drove us to monitor the electrical systems more closely. Every sensor, every motor, every battery cell was tracked in real time. And here's where things got even stranger. There were moments when the energy input readings suggested the car was drawing from an unknown source, a subtle generation of power that conventional physics struggles to explain. It wasn't just efficiency, it looked like the car was actively producing energy while in motion. Intrigued, we decided to test environmental factors. We drove through hot asphalt, rainy streets, and even windy conditions. Surprisingly, none of these variables made a noticeable dent in performance. This wasn't just a high-efficiency vehicle, It was a machine that appeared indifferent to conditions that normally sap energy from electric cars. Then came perhaps the most unnerving observation. During a period of idling, the battery level actually increased slightly. No charging cables, no solar panels, just a car sitting quietly generating more energy than it consumed. At that moment, the magnitude of what we were witnessing began to sink in. This wasn't a prototype struggling to survive. It was a glimpse of technology that could redefine transportation and energy as we know it. Of course, we weren't about to take these results at face value. We ran repeated tests, double-checked instruments, and even brought in independent sensors to ensure there was no anomaly. Every time, the results held. The car's self-charging claims weren't just marketing. They were being demonstrated right in front of us. But this left us with more questions than answers. How sustainable is this in the long term? Can it scale to full-size vehicles or even fleets? Are there hidden limitations that only time will reveal? And perhaps the most critical question, if this technology becomes mainstream, how will it disrupt industries reliant on fossil fuels and traditional electricity generation? To uncover those deeper insights, we decided to examine the car's internal systems more closely. We didn't just look at the battery and motor, we analyzed the wiring, circuitry, and even the proprietary components that supposedly enable this self-charging phenomenon. What we discovered was both fascinating and baffling. The vehicle incorporated a series of compact, highly efficient energy converters that seemed to harvest ambient energy in ways we couldn't fully quantify. Curious, we pushed the limits further. We monitored the car during extended high-speed drives, simulating highway conditions for several hours. Even under sustained stress, the battery levels fluctuated minimally, sometimes even rising slightly. This wasn't just clever engineering. It suggested a completely new approach to energy capture, storage, and management. It was as if the car was absorbing energy from the environment itself, converting it into usable power almost silently. We also tested regenerative braking in unconventional ways. Most EVs lose efficiency during repeated stop-and-go cycles, but this vehicle actually gained energy under certain braking patterns. Observing this in real time left our team stunned. It wasn't just recovering energy, it was amplifying it under specific conditions, a phenomenon we had never seen in any electric vehicle before. As the day went on, our skepticism began to fade. Maxwell Chikumbutso's claims weren't just bold, they were being validated through rigorous testing. And yet, even as we recorded data, the bigger picture became clear. This technology has the potential to redefine not just personal transportation, but the entire energy ecosystem. Imagine a future where cars don't just consume electricity, they produce it, feeding power back into homes, grids, and even industrial systems. But with groundbreaking technology comes even bigger questions. Could this be scaled safely for mass production? How will governments, energy companies, and industries respond if a vehicle like this becomes widely available? And perhaps most importantly, what does this mean for the planet if fossil fuels could finally be rendered almost obsolete? By the time we concluded our testing for the day, one thing was certain. We had witnessed something extraordinary, something that challenges everything we thought we knew about energy, motion, and sustainability. For the final test, we decided to push the car into an extreme endurance scenario, something no ordinary EV could survive. We planned a 12-hour continuous drive, combining city traffic, highway speeds, and steep inclines, all while running every onboard system simultaneously: lights, air conditioning, infotainment, and even auxiliary electronics. If the car could survive this, it would truly redefine what's possible in electric vehicles. As we set off, the energy monitors were stable, almost eerily so. Hours passed, and despite the heavy load and constant movement, the battery barely dropped. In fact, at several points, we noticed slight increases. Our instruments confirmed what our eyes were telling us. This vehicle was somehow generating or replenishing energy as it moved. The phenomenon wasn't small. It was consistent, repeatable, and measurable. During the later hours, fatigue set in, not just for the team, but for the reality of what we were witnessing. This wasn't just a self-charging car. It seemed to defy the conventional laws of energy efficiency. We began analyzing patterns. Were certain speeds or driving styles influencing the energy gain? Was there a hidden environmental factor at play? Every hypothesis we tested only added layers to the mystery. Around hour 10, we decided to simulate a near-empty battery scenario, deliberately pushing the energy levels to what would normally be considered critical for any EV. Conventional wisdom predicted a shutdown, but the car kept running. Not only that, the battery began to stabilize, as if the vehicle was regulating its own energy output to avoid depletion. It was intelligent, almost adaptive, in a way we didn't expect. By the end of the 12-hour test, we had recorded terabytes of data. Every moment, every fluctuation, every gain in energy was logged, analyzed, and cross-checked. And while we were ecstatic about the performance, it left us with profound questions. How is this technology truly generating energy? Can it be reproduced reliably at scale? And if so, how long before it disrupts not just the auto industry but global energy systems entirely? As we reviewed the live data one last time, we noticed something that made every one of us freeze. The energy readings weren't just stable, they were trending upward, even though the car had been running continuously for over 12 hours with every system engaged. It was subtle at first, almost imperceptible, but over minutes it became undeniable. The vehicle was producing more energy than it was consuming. We immediately ran multiple cross-checks to ensure it wasn't a calibration error or faulty sensor. Every independent instrument confirmed the same result. This wasn't just a car with incredible efficiency. It was operating in a way that seemed almost autonomous, creating energy in a manner that defied conventional understanding. Our excitement quickly mixed with disbelief. Could it be possible that Maxwell Chikumbutso had actually engineered a form of perpetual energy in motion? At this point, the implications were staggering. If even a fraction of this technology could be scaled safely, it could end the reliance on conventional power grids, revolutionize transportation, and potentially alter the global energy landscape entirely. But with such groundbreaking capability also came massive responsibility. How could this be deployed ethically? Could it be weaponized, misused, or monopolized by the wrong hands? Curiosity pushed us to explore one more dimension: the vehicle's response to extreme stress. We added maximum payloads, simulated harsh terrain, and even attempted rapid acceleration and sudden deceleration cycles. Every time, the car adapted seamlessly, maintaining energy levels, torque, and responsiveness without any sign of strain. Each test only deepened the mystery. How could a self-contained system behave so intelligently under conditions that would cripple conventional EVs? By the time night fell, it was clear we were witnessing something beyond current technology. Yet, even with all the data, the questions kept multiplying. Was this a prototype hinting at a new age of energy independence? Or a glimpse of a future so advanced that it challenges the very laws of physics we've relied on for centuries? What we discovered in that final observation was astonishing. Hidden within the car's design was a compact, self-regulating energy matrix, a system that appeared to draw from ambient electromagnetic fields, motion, and even subtle environmental energy sources, converting them into usable power for the vehicle. It wasn't just clever engineering, it was a completely new approach to energy generation, one that challenges everything we know about sustainability, efficiency, and mobility. In the end, testing Maxwell Chikumbutso's self-charging EV wasn't just about evaluating a vehicle. It was a glimpse into a future where energy scarcity might no longer define our lives. A future where cars don't just consume power, but produce it. A future where innovation can truly defy the limits of possibility. Whether this technology will reach mass production or change the global energy landscape in our lifetime remains to be seen. But one thing is certain: what we witness today is nothing short of revolutionary. And for anyone watching, the era of self-powered vehicles may be closer than you think.